Hello friends, so today we are going to solve 3 questions, and all these 3 questions are from our rotational motion. And the first question, it states that a disk of mass m and moment of inertia I, which is given as beta mr square, is held fixed on a wedge shaped plane of mass m that makes an angle of theta with the horizontal. The plane rests on a frictionless horizontal surface. The disk is released and rolls without slipping on the plane. Find the horizontal acceleration of the plane. In this case, we can just draw an approximate figure for the question. And so we are given a plane which is inclined at an angle of theta, and on this plane we have a disk. Mass of the disk is given as small m, and mass of this plane, wedge plane, is given as capital M. Okay. And we have to find out what will be the horizontal acceleration of the plane. So in this case, the disk is rolling down the inclined plane, so it will be moving in this direction. Okay. And the wedge will be moving towards, let's draw the, so we have this x-axis and y-axis, so the wedge is going to move towards the negative x-axis. Okay. And let us define let us suppose for a wedge motion that x of t is the horizontal position of the wedge at any time t. So you can say that the horizontal position of the wedge at any time t, let us suppose this is given as x of t, and our disk is going to move along the wedge down the inclined plane. And for that, let's assume that the distance along the slope from the top of the edge is s of t. So we say that the distance along the slope from top of the edge, from the top edge of the wedge is our s of t. Okay, it means the distance is from this top of the edge, okay, and it is along this inclined plane is excuse me, is our s of t. Okay. Now we are going to define or we can say describe our motion of the disk with respect to its center of mass, okay, or we can say the center of the disk. Therefore, we can say that motion of the center of disk and because the disk is going to move along the inclined plane and also the wedge is going to move towards our left side. Okay, so disk is going to have two types of motion that will be associated with it. One will be because of the horizontal motion of the wedge and other one will be its own motion. Okay, or we can say disk motion relative to the wedge along the inclined plane. So we can define or describe it into two ways. First way is the wedge motion, or we can say wedge horizontal motion, and the second one will be the disk's motion relative to the wedge. Relative to the wedge, and which is along the inclined plane. Along the incline. So it means the disk is going to have two motions. One will be because of the wedge horizontal motion and other one will be because of its own motion. Okay. So like we said that suppose it is moving by a distance of our s, if it moves, so we can say that if it is moving, so this is our distance s along our inclined plane and we have a angle as theta. Therefore, from here we can write that the horizontal motion, because will be moved, and we can call this as our s cos of theta, and there will be a downward vertical motion also, and that distance we can call as our s sine of theta. S sine of theta. Okay. So we can write that distance moved along the inclined plane and that distance we have said is our s. Okay. Therefore, from here we can say that the horizontal part, or we can say its horizontal component, will be our s cos of theta, and we are going to get the vertical component and that is because we have taken the coordinate as our, so this is our x and y, so obviously in the downward it will be our minus of y, so this will be giving us minus s sine of theta. Okay. Now we can calculate that our wedge motion will be like we said, it moves by a distance of x. So it means the disk also shift horizontally by the same amount, that is our x. we said that our wedge moves horizontally by a distance of x. So it means that our disk, and disk we are talking about the contact point. So it means the disk and its contact point shifts horizontally by the same amount. Contact point shift horizontally by same amount, which is our x. Therefore, we can write that the x coordinate of the center of the disk will be equal to, first is our horizontal, that is x plus s cos of theta, and we are going to get its y component will be equal to, this will be minus s sine of theta, because our wedge only moves horizontally. Therefore, there is no component of our horizontal component of our wedge. Now from here we can easily find out their velocities as well as acceleration. So if we differentiate it once, we are going to get this, the velocity will be equal to x single derivative plus x derivative, and we have this as cos of theta. Similarly, y derivative will be equal to minus, and this comes as s, and we have this as sine of theta, and double differentiation is going to give us the acceleration. So double derivative is equal to acceleration derivative, and distance double derivative cos of theta, and similarly for the y component will be same, sine of theta. So these are the horizontal acceleration as well as the vertical acceleration of the disk center. And now we can write the equation of our disk in terms of our these accelerations. Okay. So first of all, let's write, and this we are talking about only the disk, and for disk we are going to write the horizontal equation, and the horizontal equation will be our, and we can call this as the acceleration of the block, wedge, and this is our capital A, and this is our acceleration of our disk, and this is our small a. Okay. And similarly, this is also our small a. And therefore, we can write in terms of horizontal, that will be our mass into the acceleration a plus a cos of theta will be equal to, and the x component will be consisting of two parts. One will be the friction and other one will be our normal. And let me draw those components. And suppose this is the point of contact, and we are going to have a normal. This is our n, and one will be our mg. So this is our angle theta. So we can divide our mg into two components. So this will be also our angle theta. So we are going to get this mg sine of theta, and this we are going to get our mg cos of theta. And we can divide our normal also into the two components. and our friction will be our, one second, okay, we are only requiring this horizontal component, so we are going to have our, this will be also normal, and we are going to have a friction. So let me draw the frictional part also. So this is our friction, and it will be also into these two components. Okay. So we have our F cos of theta, and we have our N sine of theta. Sorry, this is vertical, and therefore we can write that our mass into acceleration will be equal to our friction and normal components, and that will be coming equal to our F cos of theta plus N sine of theta. Okay. So this will be to our horizontal components, and one second. Okay, a moment of inertia is given to us. And similarly, we can write this for our horizontal portion, and we can write the vertical equation. And the vertical equation will be giving us our m minus a sine of theta will be equal to, and this is our minus f sine of theta plus n cos of theta, and this will be minus mg. So we are going to have these two equations, and we are also given that there is only pure rolling, no slipping. Therefore we can straightforward use our relationship that we are having our disk rotation and there is no slipping, and under this condition we know that our no slipping, we can write that our minus friction times our radius will be equal to I times our alpha, and alpha is our angular acceleration and a is the linear acceleration, so we can write I times, and this comes as a upon r, and the moment of inertia is given to us, and that is given as beta mr square. So we can write this as a beta mr square times ar, and from here this r square, r and r cancels out, and we get that our friction is equal to minus beta m times a. So this is our frictional force. And now we consider the wedge horizontal equation. Okay, these two equations for our disk, the horizontal equation as well as disk rotational equation, and now we come to our wedge horizontal equation. wedge horizontal equation. And wedge acceleration we have taken as A, so this comes as mass into acceleration will be equal to minus m, we have this is f cos of theta plus n sine of theta. Okay. So these are the two our equations of our wedge horizontal motion. Okay. Now we are going to simply eliminate because we only require the acceleration of our disc as well as the acceleration of our wedge. Okay. So we are going to sort out, and let me call these equations as the horizontal equation. Let us call this as equation number 1. Vertical, let us call this equation number 2. And the friction equation, let us call this equation number 3. And finally we have a equation number 4. So we are going to use these 4 equations and solve our this for small a as well as our capital A. And for that, what we do, we multiply equation 1 by sine of theta and equation 2 by cos of theta. So we say that our equation 1 is multiplied by sine of theta and equation 2 by cos of theta. And so for our equation 1, that comes as our sine of theta. Let us discuss first of all our this left side. So we get that our left hand side, we multiply it by sine of theta. So this comes as m a plus small a cos of theta. Okay. And okay, one second, we multiply them and we add them. Okay, so this is our left hand side of first equation plus left hand side of second equation, which is our cos of theta, and the second equation is our m minus a sine of theta, and this comes as m minus a sine of theta. And obviously from here we can clearly see this sine of theta multiplied, this will be coming as a cos sine of theta, and here also we are going to get this as our a minus a cos sine of theta. Okay, and it is being multiplied by this term m. Therefore our this left hand side, we will be left with only our m a sine of theta. And similarly we solve for our right hand side, and our right hand side is our sine of theta and f cos of theta plus n sine of theta plus second equation cos of theta, we have minus f sine of theta plus n sine of theta and minus of our mg. And this multiplication also we are going to get, this will be our f sine cos of theta and this will be minus, so it is going to cancel out and we get this as n sine square, and here we are going to get, one second, this is cos of theta. So we are going to get n sine square and this will be n cos square, giving us only our n. Therefore we can write that this will be giving us our n, and we are left with this minus mg cos of theta. Okay. And obviously we can just equate them. We get ma sine of theta, so we get this as our ma sine of theta is equal to n minus mg cos of theta. Therefore from here we can write that our normal is equal to ma sine of theta plus mg cos of theta, and let us call this equation number 5. And we once again going to use equation number 1, and from equation 1 we can use our f cos of theta and n sine of theta. Okay. So from equation 1, we can write that our f cos of theta plus n sine of theta is equal to over m, and we have this as a plus a cos of theta. And we can use the equation number 4, okay, because this is our f cos of theta plus n sine of theta. Okay. Therefore we can say from equation 4 we get this as our ma is equal to minus, and this will be over m a plus a cos of theta, and we can move our common terms to the left side. So this comes as our a, and we have a capital M plus small m is equal to, or we can just plus, and we are left with our ma cos of theta is equal to 0. And from here we can write that our acceleration a is equal to minus m cos of theta, and we have this as m plus small m times a. Let us call this equation number 6. And once again we can, you can say, combine the equation number 1 and 2, and that is going to give us a relationship between our this small a. So therefore we can write this our small a will be equal to g sine of theta will be equal to 1 plus beta minus m cos square theta divided by m plus small m. So this is our acceleration of the disk. This is equation number 7. And if we substitute this into equation number 6, we are going to get the acceleration of our the wedge in terms of the given parameters, that is g, m plus m, as well as theta. Okay. And in this case, here the negative sign is only the indication of our this direction. Okay. It means we have taken that every calculation is being done that this acceleration is towards our positive direction. Okay, but it comes sign as negative, so the actual direction in which the wedge is going to move will be towards our left side. That's the only significance of our this sign. The magnitude is going to remain same, it is not going to change. Okay. Next question. It states that consider an infinite stack composed of identical massive cylinders and massless planks. Each level consists of two identical cylinders supporting a plank above them. The cylinders have a mass m and the moment of inertia is our mr square upon 2. The number of levels extends infinitely upward. All contacts between the cylinders and the planks are perfectly rough so that no slipping occurs, while the lowest plank is free to slide horizontally on the smooth table. If the bottom plank is pulled horizontally such that it has an acceleration of a, determine the horizontal acceleration of the bottom row of the cylinder. So in this case we can just draw the basic figure, and we are given that we are having two cylinders at each level. So let us consider this is our base and we are having two cylinders, and we are here above this base is our plank, the bottommost plank, and above this plank we have a cylinder, two cylinders rather, and above this once again we are having plank, and then once again we are having cylinders, and this is going to continue up till infinity. And once again we are going to have a plank, so this will be our up till infinity. And we are given that the bottommost plank is having an acceleration of a, okay, that is given to us, and we have to find out what will be the horizontal acceleration of our lowest bottom row of the cylinders. Okay, so we have to find out the horizontal acceleration of these two cylinders, and all these cylinders are identical with each other. Okay. So in this case we are going to consider this bottom two and try to solve it, and that can be replicated above because everything is same. So in order to solve this, we are going to consider that because all these cylinders are having the same radius as well as they are identical with respect to each other, therefore in place of two we are going to consider only one cylinder. Okay. So we are having, this is our bottommost plank, and in this bottommost plank we are going to combine these two cylinders to form only one cylinder, and above this we are having another plank, and then we are having another cylinder, and this is our another plank. So we are going to consider only these two, and let us consider that this is our okay, and so we are given that the bottommost plank is having an acceleration of our a. So therefore this bottommost plank will try to move, let us call this as our n plank, and this we are calling as n plus 1 plank. So bottommost, that is our nth plank, will be trying to move along with the bottommost plank towards our right side. So there will be a force, and that force let us call this as a f of n, and it moves with an acceleration, let us call this acceleration of our a of n, and it will try to rotate, that is a nth plank will try to rotate in this direction, and let us call this angular acceleration as our alpha of n, and because of that we are going to have a force on this plank, and let us call this force as our g of n, and this process will be repetitive And similarly here towards our right we can write this as Fn plus 1, and there will be a force that will be, and let us call this ever G of n plus 1. So this process is going to repeat, but we are going to solve these two parts and that rest of things can be replicated. So we consider that we treat the pair of these cylinders by one effective cylinder. Okay. So we considered that we have a pair of cylinders and that is being replaced by one effective cylinder. One effective cylinder. Okay. And if this mass is our small m, so we can say this small m will be equal to twice of mass of our single cylinder. And the moment of inertia is given to us as mr square by 2. Okay, we can deal that later on also. And now we can write, because our cylinder is going to have two two types of motion, our translational as well as rotational. So we can say that for nth cylinder, we can write its translational equation and that translational equation will be equal to our net force, that is F of n minus G of n is equal to over m times A of n. And we are also going to have our rotational about the center. Therefore, we can say that rotational obviously we are going to have our torque here. Therefore, we can write, because both the forces, that is F of n and G of n, are going to produce torque in the same direction. Okay, so we can just combine them. We can write that our F of n G of n times r, and this is our moment of inertia multiplied by its angular acceleration. And moment of inertia will be equal to b, and we have this as m r square, and we have this is alpha of n. And here this r goes by square. Therefore, we get that our f of n plus g of n will be equal to our beta times m r alpha of n. Okay. And let us call this as our equation number 1 and this as equation number 2. So from these equation 1 and 2 we can find out our f of n as well as g of n. So if we add them, 1 plus 2, g of n is going to cancel out. Okay. So 1 plus 2 will be giving us 2f of n, and that will be our ma of n plus beta m r, and we have a alpha of n. And from here we can write that our f of n will be equal to 1 by 2 and we are having m we can take as common, so this becomes m by 2 a of n plus beta r alpha of n. And if we subtract them, and if we subtract, we do 2 minus 1. 2 minus 1 will be giving us here 2g of n, so we can write this as a g of n will be equal to m by 2, and this will be coming as minus a of n, and this is our plus beta r alpha of n. Okay. And so this is our value of our f of n and g of n for our nth plank. And from this figure we can also see that our g of n will be equivalent of our f of n, because they are acting in the opposite direction but their magnitude will be our same. Therefore we can say that our f of n, rather f of n plus 1 is equal to our g of n, and we can simply equate them. So from here we get this as our f of n plus 1. Okay, we can just modify the equation, because this is equation for f of n, and it will be f of n plus 1 will be same. So we can say this as m by 2, and for this acceleration we can call this as our a n plus 1 plus beta, and we have this as r, and we have this alpha n plus 1. So here also we can assume that it is moving in this direction with the acceleration of a n plus 1, and the angular acceleration is alpha n plus 1. Okay. So we can just replicate it, and this will be equal to of g of n, which gives us as m by 2 and minus a of n plus beta r alpha of n. And here m by 2 cancels out. Okay, so we are left with only a n plus 1 n plus 1 plus beta r alpha n plus 1 is equal to minus a of n plus beta r alpha of n. And let us call this equation as our equation number 3. And this we can just replicate our to the next part. Okay, so we can replicate it this is for n plus 1, so we can replicate this for n plus 2 as well up till infinity. Okay. But we are only interested in the bottommost part. Okay. So therefore we have to solve for the first 2 planks, and that is going to sort it out. And we are given that there is no slipping So there is no slipping at both top as well as bottom contact of the cylinder. Okay, there is no slipping at both top and bottom